Okay, so hi everybody. Today we're doing a lab on thin lenses. So let's review some of the concepts from lecture that we learned about before we get into the experiments here today. So this is the first thing I want to go over, something called the focal length of a lens. What does that mean? So what I want you to picture in your head is this. We have a lens for the purposes of what we're talking about here. Let's say it's a converging lens. And we have some incoming rays that are entering the lens, and they're all parallel to one another. So these incoming rays are all parallel as shown here. We know that if a ray goes into the lens, it's going to be bent. Okay, this is just Snell's law telling us that rays will bend or change direction after going into a new medium. And so on the other side of the lens, we notice that all of these rays are now converging. They're going towards the same common point, which we see over here. And that's what we call the focal point of the lens. So the distance from the lens to that focal point is what we call lowercase f, which is the focal length. So just how far from the lens is the focal point, that's called the focal length. Okay, so when we have a bunch of rays coming in parallel like this, what you want to think of is the object that's emitting these rays is really, really far away. It's infinitely far away for all intents and purposes. But what do we do in a more general situation where the object might not be infinitely far away? It might be really close to the lens. How do we describe what happens then? Well, that's where the thin lens equation comes in. And there are three variables in this equation. One is f, the focal length, which we just talked about. The other is DO, that's just how far away from the lens do we put the object. The other is DI, how far away from the lens is the image that's formed at the end of the day. So it's a very simple relationship, 1 over DO plus 1 over DI equals 1 over F. Okay, so this is a way of predicting where an image is going to form for a particular lens. Okay, the last thing is the lateral magnification of a lens. So the definition of lateral magnification, given by lowercase m, is hi over ho. So it's the size of the image divided by the size of the original object. So if your m value is exactly 1, then your image and your object have the same size, so there's no magnification. If your image is bigger than your object, m has a positive value, so we say the image is magnified. Now, the way to calculate this is very simple. The magnification, the lateral magnification, is given by minus di over do. So we're going to put these relationships to the test in today's lab and see if for an actual thin lens, does it follow the thin lens equation? Does it follow what we know about lateral magnification? So let's do the first experiment now. Okay, so this is the setup for the first experiment. We have a bunch of different optical components on a track. So let me just point out what each thing is here. On the left side, we have a light source. It's an LED light source. And in front of that, we have a little screen. And we can put various shapes in front of the light source. Right now, there's a number 4. We can actually set this to other things like the letter L, or just a couple slits, or a circle. For the purposes of our experiment, we're going to use the letter L. Okay, so this is going to be our object. Next, we have a lens. So according to the manufacturer, this is a convex lens with a focal length of 20 centimeters. But what we're actually going to do today is measure the focal length directly and see if it's close to 20 centimeters. Okay, next, we have a screen. So what we're going to be doing is sending light through the lens and projecting an image onto this screen. And by just taking note of what distances we have on the track between these different components, we can measure DI and DO. So DO would be the distance between our object, which is this light source, and the lens. And then DI would be the image distance, which is the distance from the lens to the screen where the image gets formed. So that's basically how the experiment goes. Okay, so the first measurement we're going to make is the object height, HO. So for this, I'm simply going to measure with a ruler how big this L-shaped screen is. And what I'm getting is exactly 2 centimeters. So 2.0 centimeters is HO for this experiment. So the room lights have been cut down so we can see the images that are forming from the lens a little bit more clearly. So for this first run of the experiment, we're going to set DO, which is the distance from the object to the lens, to be 30 centimeters. And let's take a look at what's going on at the other end of the track. This is again the screen where we project the image that's formed by the lens onto. And one thing you can immediately see is that the image is inverted. So we don't see an L that's right side up. It's actually flipped around the optical axis. This is an upside down L. This is an inverted image. Okay, now the next thing to note is that I can move the screen around, and depending on where I put the screen, the L looks more blurry or a little sharper. So let's move the screen back for a while, very slowly. And notice how as I do this, the L is becoming sharper. It's getting focused. It's coming into focus. But if I move it too far back, see how it becomes blurry again. Okay? So there's some kind of sweet spot, some optimal distance there in the middle where I get a perfectly focused image of that L. And you have to just find it through trial and error. But I think that's about it right there. Okay, so let's take a look using the measurements on the track itself. The image distance is 62.0 centimeters. So for an object distance of 30 centimeters, the image distance is 62.0 centimeters. So the other thing we need to measure here for this first trial is what is the image height? So that can directly be measured. You see the image height here using the ruler is 4.0 centimeters. So remember the object height was 2 centimeters, so we're getting 2 times lateral magnification in this case. So again, image height 4.0 centimeters for the first trial. For this next trial, I've set the object distance, again that's the distance from our light source to the lens, to be 35 centimeters. So let's find where the image forms. Again, just push the screen until we get a sharp focused image of that letter L. And it looks like right about there is where the image forms. So that distance on the track, that is 47.2 centimeters. So 47.2 centimeters is going to be our image distance for this trial. The next thing to do is measure the image height. And again, we can do that directly just using a ruler. So in this case, for the image height, I'm getting about 2.7 centimeters for the image height. Okay, so the rest of the trials go in pretty much the same way. Each trial we're going to increase the object distance by 5 centimeters. We're going to find where the image forms, and we're also going to measure the image height. So we're going to continue doing this until we get to an object distance of 70 centimeters, and then we'll stop there. So rather than showing you all those trials on the video here, I'll just flash the remaining data up on the screen. So here it is. Okay, so in this next experiment, what we're going to be doing is constructing a simple telescope. So a simple telescope basically consists of 2 lenses. One of them is what we call our objective lens. This one is what we're going to be using for our objective lens. This is a 20 centimeter focal length converging lens. And then we have our eyepiece. This is what you actually look through when you use the telescope. This is a 10 centimeter focal length converging lens. So if we set these up on the track at the exact right distances, we can make a telescope which will magnify things quite substantially. So I'll show you how to set this up. Okay, so I've cut down the room lights once again just so you can see everything a little bit more clearly. And here's what we have on the track so far. On the right side we have the light source, and then we have our first lens set up right here, exactly 30 centimeters away from the light source. So that means DO1, so the object distance for the first lens, DO1, is 30 centimeters. So what we're going to do next is use the screen to figure out where the image is forming. And again, this just takes a little bit of trial and error. Move the screen around until you see very sharp focus. Okay, so that looks pretty good. And if we just read the numbers off the track, the image distance, so the distance between the lens and where that image forms, let's call that DI1, is 61.3 centimeters. Okay, so the next thing we're going to do is add the second lens, which is our eyepiece, to the system. Now the way it works when you're dealing with multiple lenses is that the image formed by one lens, so that would be the image formed right here, becomes the object for the next lens. So what we're going to do is put the second lens on the track 8 centimeters behind where that first image is forming. So what that means is DO2, which is the object distance for that second lens, is going to be 8 centimeters just by the way we placed it. Okay, so let's take a look at our telescope when it's all set up. So we have the light source on the far right side of the track. I actually put a screen in front of the light source that's shaped like the number 4. So what we'll be looking at is an image of the number 4 with our telescope. We have the objective lens, which is the one closest to the light source, and then we have the eyepiece, which we set up just a second ago, and that's what we look through to see a magnified image of the number 4. So when we go around to the eyepiece, you can see that image of the number 4. And you can also notice that it's upside down, it's inverted. And it's quite magnified. It's actually so big that you can't really see the whole thing all at once through the eyepiece. You have to sort of move your head around to see the whole thing. But there's that inverted and very highly magnified image of the number 4 using the telescope. So that does it for the experiments here today. You've got all the data you need to do the analysis. So as usual, follow along with the worksheet that I provided that accompanies this video to help you with the analysis. As far as what you're calculating, one big result that you're going to have from the first experiment is a calculation of the focal length of the lens that we were using. So according to the manufacturer, the focal length of that lens was 20 centimeters. You should be getting something very close to 20 centimeters when you make that calculation. In the second part of the lab, what you're going to be doing is calculating the magnification of the telescope that we constructed. And it's pretty apparent that we got a pretty significant amount of magnification when we look through the eyepiece of that telescope. So your calculations should reflect that. We should see a pretty significant magnification when you calculate that number in the analysis. So that's it. I'll see you in the next lab video. Take care. See ya.